One of the co-creators of WebAssembly, Luke Wagner. Luke, thanks for joining me.
Hello. Yeah, happy to be here. Thanks for hosting this.
Yeah, we were just in a meeting, literally like an hour ago, and the topic of virtual platform layering came up. And a lot of us in the Bytecode Alliance and the WebAssembly space see a lot of value in it, but I think it's kind of a new topic that not a lot of people are familiar with, and you've really coined that term in your keynote about 7 months ago now at Wasm Day in A. And I thought it'd be fun if we just sat down, chatted about it, and kind of gave an overview of what it is and why it's important for WebAssembly components.
Totally. Yeah, happy to do that.
And I'm going to do the same thing that I did last time, which is a little crazy, but also fun, and draw what you're saying while you're saying it, because I use these notes every time. And if you guys can at least see what I'm doing, then you'll know why I'm a little so maybe chaotic. So, uh, virtual platform layering. Tell me what it is, Luke.
Oh boy. Well, maybe I'll start kind of general, high level, and then we can dig into the different parts of it. So I guess you could say it's just sort of a pattern that we've seen emerge, like in lots of places in software, which is often like a source of like complexity or just hardness or annoyingness or where you have to configure a bunch of stuff. And it seems like an opportunity for us to like maybe solve the problem better and kind of more holistically, like using components and the power of compositionality. And so, I could just maybe give some examples of this pattern, and then maybe we can kind of generalize from there. If that sounds, I think that's a good
Yeah,
idea.
that sounds great.
So, so the first one that we see is, and I guess just to say what the pattern is, or generally it's like so we have this concept of a world, and worlds are like, here's a collection of things that I depend on, I import from my environments. This is like what I expect the environment to give me if I'm running it all. So they're my imports. And then I have a set of exports, which are the ways the environment calls me and says, here's, something happened, here's what. And so a world defines just a collection of imports and exports. And the key idea we have, just now fully being developed in all the component model tooling, is that we make worlds explicit. We don't just implicitly assume there's one world and we all are using the exact same one. Instead, we say, no, we're going to say what that world is explicitly. We're going to have a name, and we're going to have all the tooling embrace the fact that there can be many worlds, right? And all these different platforms, they will support different worlds because running in a client side is very different than running in a server. Running in a cloud is very different than running at the edge, running in a database, and all these things. So we're going to start by saying, we're going to have lots of worlds, and we should be empowered to like define our own new ones, for our own kind of new sorts of ways of running WASM. So that's like a foundational assumption we have. We have multiple worlds. And then we say virtual platform layering shows up when we want to take a component that's targeting one world. So this component assumes it's running in this world, and we want to run that component in a different platform that supports a different world. So there's like a mismatch between the worlds, and you can think of them, if we're layering, one's like the higher level world and one's like the lower level world in this pattern. So start off with an example. I take a bunch of source code that was written and assuming that it's just running in a traditional POSIX environment. So we have a name for that. It's called the WASI CLI command world. And so that's what the code's assuming it's running in. And so I've compiled that. It's a component. It assumes it's running the command world, but I'd like to run it in some, like, let's say, cloud or serverless world that just doesn't have a file system, doesn't want to give you sockets. It wants to give you something else. Maybe it gives you some like blob store, or wants to give you static assets or something. So how do we virtualize? How do we run this component that's targeting command world in terms of a not command world? So that's one example. Another example is like the opposite direction, which is local testing. So I take a component that I've developed to run in my production server. It's importing interfaces that are available in production, like my key value store, my SQL database, whatever else, and I want to run it locally. So in this case, I want to take the higher up world is my production environment, and then I want to run that locally where I have a file system. And so I want to somehow run that locally, and by virtualizing that world. So that's kind of going the opposite direction. But that's another fun example. Uh, Another example is, if let's say I'm building a platform for my customers, and so I just want to expose some functionality, and to my customers, it's just functionality they can import. Like, I'd like to, do some lookup or whatever. And let's say I want to implement that using WASM itself, so I don't have to build it into the trusted computing base. I can encapsulate that functionality. If I have like a bug in it, it contains the extent of that bug. So I implement it in WASM using internal stuff that is not exposed to my customers. So I want to have the customer-facing world, the public world, and then I have some internal kind of private world, which has like all the internal functionality that I don't want to expose to all my customers. So that's another form of virtual platform layering. And then lastly, when one company builds a platform on another company, which is pretty common, like you think like a Heroku builds their platform as a service on Amazon initially, which is infrastructure as a service. You can go there being like a Heroku world that's layered on top of like an underlying like Amazon world. So lots of different examples of this concept. Yeah, I don't know if that was
So
if that
that's
fit
great.
together.
I think maybe we could talk a little bit more about what worlds are, because I feel like you set the stage well for, hey, with WebAssembly components, we're building with an interface model. These are really a higher level set of interfaces. Originally with WASI, it was really more about targeting an ABI, and now we're really targeting a higher level set of APIs. And one of those higher level sets of APIs is defining an interface that is a world.
Hmm.
Do you mind talking just a little bit more about worlds themselves?
Yeah. So yeah, worlds are, show up when I'm saying like I'm writing some code that wants to run on a platform. Like how do I describe what functionality is available to me? Like, for example, I want to generate bind. I want to have in my source code. I just want to, have bindings that let me, access this functionality. Like, what set of functionality do I have? Um, we have this great tool, WitBindGen, that will generate all sorts of bindings for you automatically, so you don't have to manually do all that stuff. What collection of interfaces does WitBindGen actually produce for me? So a world kind of answers a lot of these sorts of questions, which is like, give me the total collection. And that's, from the perspective of like, I'm writing guest code that's going to run on a platform. But then when I flip it around, when from the host perspective, when I'm building a host that's going to run guest code, it kind of is the inverse question. It's like, what's the total functionality that I need to supply to be able to run this class of components? How do I call them, and what are the bindings that let me do that? So when I'm writing my host, I'm not having to do a bunch of like low level unsafe stuff. So that's, I guess, one way that's how worlds show up. And then in like a WASI standardization context, um, we want to be able to say like, what are some different classes of hosts, and to do that, and when I say class of hosts, I mean we're not going to assume like every host supports the exact same set of interfaces, but we also don't want every host to export like totally distinct, like disjoint interfaces either, because then like there's no interoperability. So we want this concept of like a class of hosts that like support similar functionality so they can run the same sorts of code. And so a way to do that is to say, okay, WASI is going to standardize some worlds, and worlds are collection of functionality. So whereas an interface is just one specific type of functionality like HTTP or a KV store or gRPC or a GPU, that's like interfaces are individual pieces of functionality. A world makes a collection of it and says, okay, here's a collection of functionality. Let's talk about this class of hosts. What are the different platforms that support this? What are, and so if I create a component and I target this world, like what are the different platforms I can run on? So it helps answer those sorts of questions by just giving us just a concept that we can name and talk about.
And so how many do you expect, like an infinite number of worlds? Are you thinking that there will be a small set of standardized worlds? That part is clear through WASI.
Hmm.
Um, but one of your earlier examples talked about, Heroku might have a world file, Amazon might have a world
Right.
file.
Yeah.
I'm also wondering, do you think Amazon might have many world files?
Yeah,
What are your
that's a great
thoughts?
question. I would say like it's hard to predict the future, right? So people always do stuff you had no idea when you're initially imagining it. But what I'm guessing now is like by default, companies are each going to define their own world. That's just going to be like, here's the total collection of stuff that you get when you run on my platform, and it's just completely the company's own choosing. Like this is what I'm going to offer on my platform, or open source projects or open source servers will each publish a world, and it's like this is all of it. And then the thing about worlds is they're kind of like Venn diagrams, right? They're allowed to like overlap and contain each other. So my company's world will contain within it various standardized WASI worlds that are like, yeah, I support that. I support a superset of that. So I'm going to like take that world and say like include that into my world. I'll pull that in. So yes, I support that, and maybe some more, some stuff that hasn't been standardized yet, or maybe get standardized in the future, or maybe stuff that just is like, no, it's just super specific to just me. So like it's only ever going to be in this one world. So world per company, and like kind of open source server sort of project starts to make sense in addition to these standardized worlds. And then who knows where things go from there. But lots of them, but not like millions, right? Not uh, thousands, maybe is even a stretch. Hundreds would be kind of a lot. I don't know. Well, hundreds, yeah,
I
starts to make
mean,
sense. Well, lots of
if
companies,
we
right?
if we get there, right, that means that we're being wildly successful, which is
Yeah,
awesome.
right.
But it always helps to kind of understand, kind of grapple with the shape of things.
Hmm.
Okay, so that part makes a lot of sense. Now, breaking down the term virtual platform layering, you've talked about how the idea is that you have different worlds and then you kind of layer them on top of each other. So the platform
Hmm.
layering part makes a lot of sense to me. Can you talk a little bit more about the virtual side of this?
Yeah, you bet. So the key thing there is when I implement the higher layer, the higher level world in terms of the lower level one, the way I do that is by writing a component. And so yes, I'm running components in the higher world, but I'm also implementing the lower world also with components. And so it's just components linked to components. And so the virtual part is I'm able to kind of I don't have to implement a world. I don't have to implement this in the native code. In like if I'm implementing my server in Rust, that's or C++ or all the normal implementation languages. I don't have to do that. I can just use any language and compile it to a component. So I have that same kind of degree of safety and isolation that I have when I'm using components. I have that even when I'm implementing higher level worlds.
I took advantage and assumed that most folks probably already know what WebAssembly components are. It might help to break it down when we talk about why are WASM components safe to use? Why would I want to write a WASM component that I virtualize for a given platform?
Yeah, it's good. We should start there. Yeah, so yeah, what's a component is basically you would say like, well, what's WASM's version of a container? What's like a nice distributable, publishable, reusable unit of code? And you're like, well, a container isn't quite right? Because also we want to know what's the dependencies and kind of the exported signature, like the exported interface of this component. So maybe say take a container with an open API, glue those together. That starts to get a little closer to what a component is. But we also want it to be like a lot lighter weight, so they're like really fast to start up and also portable, so they can run on a bunch of different hardware and a bunch of different operating systems. So that's what we can do to improve upon this kind of starting point. But like if your basic intuition is like a container with an open API, that's not terribly far off. Um, but at the same time, also, like what's the developer experience of using these things? We want it to feel kind of like modules and packages. So when I'm using a component, I just want to write import if I have a language with a module system and it has an import statement. I just want to write import and import this component, which is kind of pretty different than the way you would talk to another container, right? So I want to make it feel like it's a module, like when I'm writing code that uses this. So we're trying to like almost take a midpoint between modules and packages on the one side, which are like kind of normal developer facing artifacts, and the containers on the other side, which are kind of more like operational artifacts, and then sort of say like, what's like a meeting of these two concepts? And so that's another way to think about what a component is.
I
Also, they're
like
language
that.
agnostic. So when I compile a component, you don't really know what language I use to implement that thing. It's an encapsulated detail. I'm speaking through an interface that's written in an IDL that we define in the component model called WIT. So I'm writing my interfaces in a language agnostic way. And in that way, I can also generate bindings in all different languages from a given interface. So I author my component once in whatever language I want, and then all the other languages that use my code get to generate their own bindings in their own language from that interface. So where I'm getting also some cross-language interoperability here for free. And then getting to the security part of you mentioned, components are kind of encapsulate their low-level state and don't have access to each other's state. So if I have two components, one can't reach into the other one's memory and just pull out some stuff. So this is how they're different than kind of like DLLs or just like normal modules in a normal programming language. Well, depending. Where there's no shared global state. A lot of module systems have like a shared global object and they can kind of like collide and mess around in that shared global state. And components don't have that.
Um, could I have global state if I wanted to for a component?
Yeah, great point. So you could, and the way you would express that is by importing some sort of shared like data store. So if you had two components importing like a database, that's a way for them to work with each other. But at least in that case, we're doing it sort of explicitly and through like a declared interface that hopefully we can scope and reason about and say like, okay, yeah, that's the state we're sharing. Yep, that's what I mean to do, as opposed to like, it's all free game. They're all just bits. Touch them.
Yeah. Okay. So all of that makes a lot of sense. How does this relate to WebAssembly modules?
Yeah, great question. So that's kind of like our building block. That's our foundational primitive, which is core WebAssembly defines this concept of a module. A module contains a bunch of basically instructions and code I can run. And so you can say what core WebAssembly does is it gives us portable instructions that can run on any CPU. But very, very much by intention, core WebAssembly is very low level. It's trying to be as low level as possible, but no lower, which is to say if security or portability aren't in the way, WebAssembly wants to be as low level as it can. And so a core module is sort of like a portable DLL. It's sharing memory. It's just a bunch of pointers and a big shared array of bytes. So it's a lot like a portable DLL, which is great. That is a great foundational building block. You want to have that in your system, but DLLs are not like our unit of cross-language interoperability. They're not a great thing to distribute and share code, and especially and they don't go between languages. So you want to take kind of that starting thing, this core module, and then wrap it up with some higher level interfaces. So component interfaces are trying to be as high level as they can, give us nice things like lists and strings and records and variants and resources and handles to these resources. These are the things that make sense when I'm talking about like language interfaces and interoperability. And so component models is wrapping that up in this nice high level interface, but in the guts of that component is just a bunch of core WASM code poking at bytes. And so we can um, keep these concepts separate.
Yeah, what I often call them, I say that a WASM module is really a bunch of numbers in a trench coat. Because if
I
you
like it.
if you look at the types in WebAssembly, they're just numbers, and so it's kind of like your pure compute. And then when you think about WebAssembly components, they wrap a WASM module, and then they give you that language interoperability layer, but through a declarative interface, so that they can interact with each other. Um, I think the thing that I'm most excited about is this idea of being able to bridge different language ecosystems. I think that is going to create like an entirely new, I pun intended, world of software engineering. What uh, what would you say is one of the key motivating factors for working on components, but specifically in virtual platform layering? We can go back to our original examples, but I think we should talk about like the key pain points with these, right?
Yeah,
Why would I necessarily want to do this? Because I've been doing local testing all along, right? We can
yeah,
start with that one.
yeah. No, yeah, great question. Yeah, you're right. People do all this stuff today, right? All those are examples of things people do today. And I guess the observation is it ends up being a lot of work, and you have to kind of roll up your sleeves and write a bunch of like low-level tools, kind of tailored to each individual situation. And so there's a lot of repeated effort, and there's a lot of like kind of hard, bugs are made, and you get you don't have, since there's not a lot of focused effort on a shared thing, the quality of each individual thing maybe isn't as high as if everyone worked on a few shared pieces. So I guess you could say that's a theme of the component model. Where like, what if we pooled resources, work together on really high quality bindings, work together on some of these hard problems? And so this is one of these hard problems where if we pool resources, we can have a really good file system virtualization layer that says, all right, you want to virtualize file systems, I want to virtualize file systems. Let's all work together on this and say, okay, let's have some shared code for how do I virtualize, how do I mount a blob store into a file system? How do I take static assets and really efficiently pack them into a component and implement them, use those to implement a read-only file system? What are the different like caching and write back, and all sorts of what are the knobs I want to expose and work on those together? And so yeah, so I guess we're trying to pool efforts here, um, so we don't everyone doesn't have to reinvent the wheel repeatedly.
Yeah, one of the realizations I had is that by creating the suite of components that are taking advantage of the virtual platform layering pattern, we're going to get to a place where just about anybody could run their own cloud safely because all of this is going to be virtualized. We're going to be working on it together in a multi-vendor way. A lot of this work, for example, will happen under the Bytecode Alliance, where Luke and I are members of, and that will let people build their own cloud, but then focus on that one place where they want to specialize.
Mhm.
Um, do you mind talking a little bit more about how you would choose when to virtualize and when not to?
Yeah. I guess it starts by saying like I should be able to think of like what's the interface I want to expose to my usually I have some sort of customer or guest or plugin or some sort of code that I'm running. I want to start by just thinking like what's the right interface? What makes sense? What gives me the system the right abilities and what gives the guest code the right abilities? So I want to design that system without having to think and be overly worried about, oh, but if I put all that into the system, then the trust computing base gets really big. This is going to be like a security risk. I want to be able to say, no, that's the right interface. And if I want, I can implement it as Wasm or implement as native code. And so the trade-off there is, if I do native code, maybe I can do some cool low-level stuff. I can like reach down deep into like the kernel or write some custom like driver or integrate with some other like native system and do some shared memory stuff. So maybe I want to do that. But maybe I don't want to initially do that. Maybe I want to get a mock implementation working quickly, write it in whatever language I want, compile that to components, and use that to implement my interface. And then as people start to use it, as I profile it, I say, oh, this is hot code. Maybe then I rewrite it. And if I've separated out this idea of okay, I'm going to define the interface and say the guest is on that side of it, and they can't really see through this abstraction and know is it host code or is it implemented as a component. If they don't know, then it gives me that flexibility later on to kind of shift code and refactor and rewrite as I choose based on performance and how my system evolves. So I guess yeah, that's I guess you would probably start by defaulting to just do it in whatever's way is most productive and lets you get put something out there so you can get feedback quickly, and then over time you may choose to rewrite different parts in native or not.
Yeah, I think that highlights well one of the pain points is that when you're a cloud provider, Luke, you work at Fastly, I work for Cosmonic. We are running other people's code. They're sending us their arbitrary code. It could have all kinds of gremlins in it, and there are all kinds of different ways to cause exploits. And so we don't trust it, and that's why we're interested in using WebAssembly. It's why WebAssembly is, in my mind, the last plugin model you'll ever need. It's the best way to just run other people's stuff safely in a sandbox. But when you're implementing a host, you want to give capabilities to people. There's a lot of things that they expect. So by starting with something that's virtualized, but maybe not optimized, we're able to protect ourselves and provide that safety guarantee. And this type of virtualization, it ties right back into what you were talking about, how we're able to pool our resources together. I need a virtual file system. You're going to need a virtual file system. Everybody needs a virtual file system. So, by us working on these common components that are language interoperable, so any language ecosystem, somebody building for Python or building for JavaScript or Rust, they can import this one component, the same component across all of these different language ecosystems, eliminating like these huge silos. Like this point I don't think ever quite people get it because we're just so locked into I'm a front end engineer and I work on React. And you Angular people, like even if they're a front end engineer but they're working on Angular and not React, you're like, get out of town. We can't share code. That's impossible. Uh, and I think it's going to really change the game.
And it's pretty hard to virtualize right now. Like if you look at the existing units of code, there's such a thing as containers, of course, exist, and you're like, if you look at a case where people are virtualizing a lot, service meshes, and it's a huge amount of work and a huge like activation energy you have to get over to make that leap and how do you do it? It's with a lot of work to like intercept a whole socket and decode it on the other side in the sidecar proxy, and then you can start to like virtualize and say, oh, you think you're speaking TCP, but actually I'm doing MTLS on you, you know. And so that's virtualization. That is actually virtual platform layering, but it's so hard, and it has this really high performance overhead. So maybe what's kind of maybe new this time is what if we design for virtualization kind of from the beginning and make it really low overhead and make it actually kind of easy so we can do it like a lot more in a lot more cases. What if it wasn't like such a big lift?
I love
And then
that. That's a great example. I think a lot of people maybe aren't. I mean, a lot of people are familiar with the sidecar pattern, but maybe others aren't. And so, what Luke was just describing there is a very popular paradigm to support polyglot microservices. So some microservices written in Go, some written for Java Spring Boot. They will typically be in their own container, and then there will be a sidecar proxy container that sits right next to that container in a pod inside Kubernetes. So they're running in the same space. And when an HTTP request comes in, sometimes you want to terminate the TLS or add different types of middleware headers and interpolate what somebody needs to do with that type of request with a common library. And so a really common pattern for trying to solve things in a polyglot way is by adding this sidecar container. Last time I checked, a lot of them are, in terms of size, like megabytes in size, and then you've got these spread across say a fleet of microservices, so 100 of them. Now you have also 100 little sidecars, but they're there. They're adding costs. They're not run in the same process. And so with the component model and this exact paradigm with virtual platform layering, we have it running in the exact same process, right? That's all in the same component that's linked together. And we can add that type of middleware work in a common way that maybe we even cache just that one piece, that one part of that component in the host. And then that host might be running many of these different components. Like, this is such a great example to dig into. I love it. It's juicy.
Totally. And it feels like there's also, when designing interfaces, like you kind of want to go with the highest level interface you can that abstracts over as much as you can, except for the essential task you're trying to solve. And so if you can have a really high level interface and then say, oh, but the implementation, yeah, I have a component that implements that high level interface in terms of an HTTP API. Like, I'm giving you these higher level verbs that are like specific to my application, but I can start by just implementing terms of HTTP. But then over time, without changing that high level interface, I can swap out how I implement that and say, oh, actually there's some different protocol, or actually I can do something smart and not even speak over HTTP at all, do something locally inside the process. And so by defining that layered world that has the highest level interface I kind of preserve that optionality in the future. So I kind of, as a person who's defining the platform, I give myself a lot of leeway without having to put a bunch of code in my trusted computing base.
I love that. Like, you could do HTTP, but also not really, right? I So many things we'll be able to bridge, right? Because we have all started building up with RESTful APIs, and all of us just kind of assume HTTP is there. But if I do an analysis of my stack and it's like these same three microservices that are always talking to each other all the time, why not run them local? Why not run them where they're on the exact same network, and let them still have the right decoupling between each other, be able to update independent of each other, version independent, and have a strict API contract between them, but get all of the benefits that you get of having one process that's running locally for performance. That is huge. I wrote Mind Explosion because that's where I'm at. So I want to go back to more problems, right? Okay, so
Yeah.
we've talked a little bit about local testing. I think you've basically answered this, which is there's a lot of work involved in being able to do local testing. You mentioned mocking, there being able to do A/B testing, pointing to a database that's not the for realsy production database. A lot of that can have a lot of costs associated with it too, to test it like fully end to end in the right way. And being able to take that exact same component binary and move it between all the stages of local to dev to prod is really powerful. It'll save us a lot of time in it, and we could even generate a lot of the testing patterns because we know what the APIs are. So now we can generate this whole suite of fuzz testing around it. We can even have a fuzz testing framework that everybody is able to share, which is huge for the industry. Um, I want to talk about maybe what are some of the problems that we get when people are assuming that source is written for POSIX, and we want to run it in the cloud. Like, what today everybody writes for POSIX. Is it really a problem? I'll start with that.
Well, not really. I mean, I guess this code works and we want to keep it working, right? So that's not a problem. I guess the challenge is like, how do I implement that effectively as a host? Do I implement a file system and then does it stick around? Do two different guests share the same one? Do they each run their isolated one? maybe I want to default to isolation, but in some cases, maybe I do want them sharing. So now one does not simply, so I want to maybe virtualize this file system. I would have different mounts, and this thing is mounted to this, and this thing's mounted to that. And then when you mount things, there's a bunch of different options. And now I, as the host, am making all these decisions that have all these like huge impacts on my guest, and all of this seems like, well, could I just let the guest control this? Can I not let the guest have a lot more power and say, look, I'm going to say what are the high level APIs I actually, the real APIs that I actually want to give, like a blob store, a KV store, and I can do some things with static assets. Can I not say, like, that's what I'm going to give you as a host. You, as the guest, can have a lot of power in how do I virtualize up my own file system. And so if I have some weird need, or I want to like make some strange configuration, I can do that because it's just client side tooling and tools to like build this stuff. But if we just like throw up our hands and stop there and say, like, okay, do your own file system, that's actually hard, right? There's a lot of work that goes into that. So this is where it comes back to, like, can we have some shared tooling for, I'd like to factor out like a file system virtualization tool that says, okay, so you want to virtualize a file system and you want to do this as part of your like developer build step. Um, can we have a shared tool that can be used across different language ecosystems? So it's not like specific to like JS or Python or something. When I'm writing JS, I can just like import WASI file system and just use that like normal. And then and so that gets one component. And now I want to like virtualize that file system in various ways that I want to configure. And that can be this separate step that uses a tool that's shared across these ecosystems and has a lot of work put into it. Um, yeah. So uh, that's factoring out the work of what is that tool. Now, this doesn't exist yet. This is, I think, a thing that you were just saying earlier today. We need to get started on, because the primitives are now just coming into place now-ish. So now it's even just starting to be possible to write this tool. So yeah, this is I think an exciting next thing that we do want to pool our efforts on and start some sort of Bytecode Alliance project about. Help me virtualize a file system in the many different ways that I might want to do that. Let me control that as the developer. Who knows what I want, and not just file systems, but also sockets is another thing. There's a lot of code out there that speaks sockets, and a lot of platforms that don't natively give you sockets. So how do we a tool that can virtualize sockets in terms of things that aren't sockets? And there's a lot of ways to do that, a lot of configuration options. That should be part of this same tooling, which is really like, help me virtualize a traditional POSIX view of the world in terms of like a more modern cloud, serverless, edge, whatever platform.
I love it. Yeah, I think that this will be a great place for people to get involved if they're into it. Actually, I should probably include a link, but brightcodealliance.org is a great place where we've got a large community of contributors. I think last time I checked, we're around 100 now. And we're working on building secure software foundations, including tooling, compilers. There's runtimes, and then soon, yeah, virtualized components that give you all kinds of goodness that everybody, I think, is going to start building on top of, which is like, for me, it feels kind of like when containers just started, and people started building different types of containers that they shared and pushed up to Docker Hub, like having a shared registry and adding things for the first person who got a database put in a container, right? At that time, everybody just started building on top of that stuff, and it just became a commodity. And it's really exciting that we're at that point. And so, yeah, please join us. I think that is my main point. There's one other thing that I wanted to go back to for the POSIX side of things. And you had mentioned that in your keynote before about if everything looks basically like a socket in a file system, how are you able to secure that, right? That's kind of what a typical POSIX application looks like today. But in the future, what we're kind of imagining is that we will have it really down to exactly the API that you need to use. If I'm talking to a key value store at a POSIX level, I'm still talking over a socket. But from a component model perspective, I might be using the interface for a key value store, and I'm allowed to do that, but maybe I wouldn't be allowed to just open up a raw socket. Are there other things that I'm missing there that I think we should highlight before we're done? Oh, and we've also got some questions coming in, but I'll pause there and then we'll go to questions.
No, you covered a lot of good things there.
Okay, so we've got one question coming through. I'm going to See if that works. That works. Okay. Some people that I've talked to, and I'm reading the question out loud, concerned about the complexity of the types and the bindings that are in the component model. And it is more complex than, say, like RPC calls. Um, I think that uh, the question specifically here is how complex do you think the component model needs to be in order to meet these goals?
Yeah. Yeah. I mean, it's definitely a goal to try to make it as simple as we can. um, there's the value types, and if you look at our set of value types in the component model, they kind of match almost one-to-one ish with what you would see in like gRPC. With the collection of like you have some sort of lists thing, you have something with like a union, or we call it a variant, and records and strings and various numbers. And so the value types is actually, I would say, comparable to a lot of IDLs that you would see. The interesting thing that's a little new and different is how resources and handles work. And that's not a thing you see in a lot of RPC systems, because RPC systems fundamentally, like kind of by the R in them in their name, are remote. They're talking to another machine across a network. When we're talking about linking two components together, they're not across a network. And one of the basic design goals of the anti-goals, I guess, of the component model is we're not trying to be magically distributed. That was tried in the zeros, and it failed for with your DComs and other that generation. And people just said, oh, distributed computing is not a thing you can abstract over. So let's not try to do that again. So when we're linking two components together, they're running in the same process roughly. They're running the same partial failure node. If one traps, they all trap together. If the machine crashes, they all crash together. We're not talking about partial failure. And in this mode, it makes sense to talk about handles and resources, kind of like we can in an operating system when I can take a passive file descriptor between two processes. So a handle is kind of like that file descriptor. So that's a thing we have and can talk about with components that RPC systems can't really. They do pass URLs around, but URLs are a different beast. They don't have a lot of the same properties as like a file descriptory sort of thing does. And so in the component model, we're trying to talk about ownership, exclusivity, and of these things, which ultimately give us performance, and also avoid bugs where two people think they have exclusive access to the same thing, but actually they're clobbering each other. So those sorts of problems that show up when you have kind of local sort of mutable state. So yeah, those are things that are not in RPC systems, because they're kind of out of scope for an RPC system, that are in scope for us. But it's new, and so it is kind of a new source of complexity. But I guess the bindings here, we're going to work on them to try to improve them over time, make them as simple and ergonomic as we can. Um, yeah, I think there's just some more work to do here, and but also some of it's just a tiny bit new, just because of people. We may be the first people to focus seriously on sub-process isolation. So yeah, maybe that explains some of it.
I mean, the bleeding edge, which is what this is. Sometimes it bleeds. So yeah,
Yeah,
it's a little sharp right now, but I have two thoughts
certainly right
here.
now.
Um, there are a couple key differences between RPC systems, right? RPC systems, by their nature, requires you to serialize and then transmit. And even if I was doing an RPC with something that's running local and having two different processes communicating, that's still a performance penalty that you won't be paying with components. Originally, I guess in 2019, there was this really cool blog post that was published. I think Lynn wrote that one, Lynn Clark, but it described the nanoprocess model, which is that kind of that idea, and using the idea of being able to pass around handles rather than the entire serialized type between different components is really valuable, I think, in terms of performance and scalability, and getting us to some of these more language interoperability goals, which you couldn't easily do before with RPC calls. That's something that we've all been kind of trying in the Wasm space for a while with Wasm modules. Is I'm a maintainer on Wasm Cloud. We literally use the RPC model, and what that kind of forces you to do is have language bindings for each language. You're kind of rolling your own thing, and all of this is kind of going back to, hey, let's design this together as in a multi-vendor way, so that we're able to do this. But also, what's the big idea here? And I think it took a little while, a few years, to figure out what that big idea would be. But I would say in the last year, it's taken shape into what we now call the component model, which is really, it's really cool. Um, And you hinted, Luke, a lot about ownership and exclusivity here as being valuable. I think there's probably a lot to talk about between going between the component boundaries. Is there one resource that you would tell people to look at if they wanted to learn more?
Um, there's not a great one. It's in low-level sorts of state in the explainer, but we have a lot more higher-level documentation, right, to explain this better. And once the language bindings are actually fully built and working, then just writing some real source code examples just in normal languages. Right now, you have to kind of look at the assembly language level, which is pretty rough. So there's not a great thing right now, but you would look at the component model explainer, has these own and borrow types, which are sort of like dynamic versions of Rust's concepts that are similar. But they we think I think we know how to make them work in even like dynamically language contexts where these patterns already emerge like naturally and like in the web platform, in terms of like unique ownership of various objects and transfer of like array buffers and that sort of thing. So I think we'll be able to just make them feel like uh, normal dynamic language things. But
Another
there's a lot more that could be said about that.
Another point on the complexity front, I feel like what we're working towards right now with the project Wit BindGen is that, and a lot of the pieces that are inside the Wasm Tools project and the Bytecode Alliance, is that we're moving that complexity away from all of these different Wasm vendors and into a shared piece for figuring out how to solve this for each language. And so it's new and probably has plenty of rough edges right now, but I hope that like a future state, maybe a year, is that um, somebody's writing code and it doesn't feel unnatural. It feels native to be pulling in these different components. It'll come through their package manager within their same ecosystem primitives, and everything will kind of it'll feel just right. And back to what you were saying before, it'll feel like you're working again with modules and packages. And so once we hit that point, I think it'll be less about the complexity at the layer that users are going to hit, and then we'll be solving a lot of different interesting problems, I think, at the host level.
Totally. Getting to where we're working on the interesting problems and not all refiguring out like how exactly do we figure out like these low level ABIs is a good step.
I mean, every era of computing, it feels like, we do this big move to some cool new infrastructure thing, from VMs to containers to Kubernetes to serverless or Edge, all of these different places, right? We do this big lift, but every time that happens, there's also this like jump between different languages and ecosystems and ways of writing our code. And I do feel like this is the next wave of computing. But like a side goal is like maybe we've come up with a way to not have to do this again, where I don't have to rewrite my code from C++ to Java back to C++ to uh, Flash to maybe JavaScript for a while, and then compile that into Wasm, and then anyways, that's a real story. That is actually one of my development loops that I've been through. Is that like one piece of code from the '90s has made its way till today, is now in a Wasm module, but. If we build the software foundation that lets us eliminate language ecosystem silos, then we can actually, finally start focusing on the real problem that we're trying to solve, that new next wave of computing, why we're moving to that, and less so on worrying about what language we're using, because
And
we'll
just let
finally be able
people
to just
choose the
use the
right
right thing for the
tool.
job.
Yeah, I
Yeah,
was going to say the
exactly.
exact same thing.
Yeah, right. Let's end on that.
And if you think about the job of a, sorry, you said end on that, and I was like, but
No,
if
no,
you think
go,
of the
go, go.
job as a new language designer, it's if if you have to go about it without a component model, you have to figure out how to integrate with 100 different places now, each of which are like have each of those places have personally specialized their platform to existing languages. So if you're a new language, it becomes an increasingly insurmountable hurdle to get down to get over to like get your language adopted. Whereas if we can get people decoupling this and saying, okay, we're writing our languages, our interfaces in these high level bindings, bring your own language, then it means that you can actually just focus on actually designing your new language, and then you can run in all these places without them, each of them having to like embrace you one at a time and custom write all their bindings. So yeah, hopefully it improves, it gives us some more language choices over the long run too.
Luke, I can't stop. Every time I talk to you, I just want to keep making it longer and longer. What you just said makes me want to talk about how I think we're going to get some pretty cool and weird languages because imagine you're no longer trapped in trying to make it work with LLVM or C, so you can reuse all these existing things. You can just get really weird with it, support components, and then everybody's able to use you. I'm not like right now when I'm thinking about writing a CLI and I want other people to use it. I have to consider like, okay, Go people only want to really work in Go, and they won't use it. But maybe that's who I'm targeting is somebody that's very in the cloud native space. But maybe what I'm doing is more systems level, and I think I can nerd snipe a REST station a lot easier. So I should probably write it in Rust. Like I have to think about those things right now, and it
It's a
would be
whole
great if I
extra
was just
concern
focusing on my
matrix.
thing.
Hmm.
Oh,
Totally.
hey, we've got one more question.
Yeah. Do you think
Could
we
you
have time to go
comment?
into this?
Yes, I think we
All
do.
right.
Last question, and then and
Right
then
on.
then we'll wrap it up. Can you comment on the component model's approach to concurrency?
Yeah, no, there's a whole lot to unpack there, and then in parentheses threads. So one thing is we're trying to kind of decouple these two things we want: concurrency and parallelism. Parallelism is I want to run faster on more cores, as you give me more cores, and concurrency is I want to do a bunch of stuff at once, like streaming in requests and responses as streaming them out, and doing all these things interleaved. So we're all doing concurrency a lot of the time, especially in a cloud context. We don't all necessarily need parallelism all the time, or oftentimes we're getting it for free at a higher level just by using the serverless paradigm. Tons of parallelism in the host. The host is able to run, millions of requests in parallel because they're all isolated from each other. So we almost have just with serverless at all, we have like just a bounty of parallelism. So, but it's the concurrency that's much harder, which is I want to write a single guest program. It's processing a bunch of like incoming and outgoing streams. It's kind of like the hard, maybe a simplification of the summary of what I'm doing. So to do that, we started by saying, okay, what if we try to just solve this at the WASI level, just have various interfaces that kind of just do something. And all of these end up having a lot of trouble doing things composably. You can do a thing that solves like a lot of the problems, but if you want something that's like high quality with high performance and does back pressure right and is cross-language composable, we kind of ruled out all the other options other than just basically building into the component model as just first-class concepts. So basically, our approach now, which is proposed in at the to-do section at the end of the explainer, sketches out, is to just add in two types: a future and a stream type, a future of t for any t, including other futures, and a stream of t that has a final value of a u, so for any t and u. So these are just built-in types, and the idea is we have a pretty good idea of how to map these future and stream types into a bunch of different languages. For example, a future should turn into a promise in JavaScript, just a native promise, and a future in Rust. And stream should turn into like a readable stream in JavaScript and a stream in Rust. And so the idea is these are types that have a pretty good binding into a whole lot of languages, and you can always fall back to just some sort of like callback function pointer looking thing if you don't have anything at all, like C does. But for a lot of languages, you'll be able to bind to something much nicer and much more integrated with your language. So these types, by making them like just first class component types, just like list and string, they can, the bindings generation that we're putting all the shared investment into can just do the really hard work of binding to, your language's concurrency model. So we should be able to bind to event loop concurrency, but even also the kind of more recent like coroutine end-to-end sort of scheduling or threading green threads approaches too, like you have in Go and Kotlin. So yeah, there's a whole bunch more to say about futures and streams, and then once we have them, a lot of interfaces that you currently see sketched up in WASI will just get a whole lot cleaner and nicer, and you'll just say like, oh, that just returns a stream, or that you know. Consuming a response just returns a stream U8. Creating a response just passes stream U8 to the constructor, and things should kind of just work. And in JavaScript, will just use a readable stream, and it'll just work. So that's roughly the goal.
Luke, would you say that the design is basically a structured concurrency design?
Yeah, good point. Good, good connection. That is another thing that we're going for, which is structured concurrency. Which is, what does that even mean? That is still, it has not been, I wouldn't say formally defined yet, but there's sort of a fuzzy definition, which is when I call a thing, it doesn't just keep running without me knowing and allowing it to keep running. So it doesn't just fire off some background thing that's just kind of running off in the future. It's when I call you, you get to you get to keep running concurrently, but I get back a handle to that running computation, which is either the future or the stream. And I can know when you're done and wait on you finishing. And so there's this sort of the tasks you spawn make a tree, and children finish before the parent task is done, and you can kind of have this all the way up, and it has various nice uh, properties. It gives you a lot of nice composability things for free. It helps you reason out your programs and their correctness. Um, yeah, there's a lot to say about structured currency too.
Maybe we could have just another fireside chat just around that.
Oh yeah.
Obviously, we need to have it take shape. A lot of our plans for futures and a lot of the async behavior, I think we're skipping that more towards what we're calling WASI Preview 3, which
Yeah,
likely isn't this year. We're focused this year
it's a
on
next year
WASI
thing.
Preview 2, right?
Hmm. Yeah, so we're in preview 2 timeframe. We're doing the best we can, just using resources, which are already, it's a step up. We've resources takes one giant leap past, what we were doing before. And then, but if we want to do composable, high performance, good concurrency, we're going to want, to not stop there and carry on to preview 3 next year.
Excellent. All right. Well, Luke, as always, it was a pleasure. Thanks for hanging out with me. Thanks
Oh
for
yes,
letting
super
me
fun.
talk you into hanging out with 1 hour notice. So I appreciate it so much.
And impressive job talking, typing, drawing, all these things at once. I'm
It's
always
fun.
impressed.
All right. Well, thank you, everyone. See you next time.
See you next time.